Good evening, everyone. So, welcome to the third week of Matlab-Based Programming Lab in Chemical Engineering. Let's wait for like few more minutes so that more students can join, and we'll start the today's session in like 2 to 3 minutes. Okay. Good evening, guys. So let's begin today's session. In this week's session, we tried solving a problem which involved finding the head loss due to pipe friction. So we'll try to give a quick recap on this problem. So in case you have any doubts or something, you can ask me. I'll be discussing the code also. And now, then what we'll do is we'll pay attention to like the few parts of this question, which will be using some inbuilt MATLAB functions, and we'll try to solve more questions that will help you solve your assignments. So before starting the session, do you have any questions to begin with? Okay, so if not, let me start the session. So the question that we discussed this week was, it is required to pump 98% sulfuric acid at a flow rate of 5,400 kilogram per hour through a pipeline system having 5-inch diameter pipe of total effective length of 375 meters. And this question has three sub-questions. So the first thing what we have to find is determine the head loss due to pipe friction. The second one is examine the effect of Reynolds number on the frictional head loss when Reynolds number is between 500 to 1,500 and when the Reynolds number is between 5,000 to 25,000. So that is the first 500 to 1,500 falls in the laminar region and the 5,000 to 25,000 Reynolds number falls in the turbulent region. And we need to understand how this frictional head loss behaves in the laminar and the turbulent region separately. And next is generate your own Moody chart for the turbulent region. Okay. So first and foremost, the things that we have to keep in mind is that first, the kind of solution that we're discussing is 98% sulfuric acid. Let's imagine there is 2% water or something. And please keep in mind the units also. So if you see the unit, the flow rate is given in the unit of 5,400 kilogram per hour. And the pipe diameter is given in inches. And the total effective length is given in meters. See, so the thing is, these three are in three different unit systems. So you have to bring everything together into one unit system before starting your problem. Okay. Otherwise, you might make like some silly mistakes. So the first thing you have to do is if there is a different unit system that has been used, you have to convert everything into a single unit system. And the next is we'll try to calculate the first head loss due to pipe friction. So let's first convert in the mass flow rate. So the mass flow rate 5,400 kilogram per hour can be converted into 5,400. Let's divide it. Just give me a second. I'll just divide it. So 5,400 uh, divided by 60. So that is, I think I made a mistake. So this is supposed to be second, okay? Divided by again 60. So this unit is different. Sorry for that. I'll just correct it here right now. So this is kilogram per second. Okay. So the first unit has been converted. So the 5,400, you have to divide it by like 60. Then it will become then it will become 90 kilogram per 90 kilogram per minute, and which has to be again divided by 60. So basically, this quantity you have to divide it by 3,600. Okay. So when you divide that, you will be getting this unit as the mass flow rate G equal to 1.5 kilogram per second. Next is this inch has to be converted. So 5 inch, if we convert into meters, it comes as 0.127 meters. And the next is a total effective length. If you're converting the total effective length of 375 meters, so the unit is same. Everything is in the SI unit system. So the length can be kept as 375 meters itself. Now we'll come to the formula where you can find the head loss due to pipe friction. So basically, the head loss due to pipe friction is calculated by this given formula. HF is the head loss, and this is the friction factor. F dash is the friction factor. L by D is the pipe's length by diameter ratio. U is the velocity in which the flow is happening inside the pipe, and G is acceleration due to gravity. So the entire formula is HF is equal to F dash L by D U square by 2G. So in this, there are certain things that has been given to us, certain things we have to figure out. For the first thing is, do you know the friction factor? No, we have no idea what the friction factor is. Do we know the length of the pipe? Yes, the effective length of the pipe is given as 375 meters. And the next is diameter of the pipe. Is the diameter of the pipe given to us? Yes, that is 0.127 meters. Next is the velocity of the pipe. So the velocity of the pipe is not directly given to us, but we can find out from the flow rate. Okay. So from the flow rate, we can find the velocity of the pipe, and then it is divided by the acceleration due to gravity, where G is 9.81. Okay. So here the only unknown is the friction factor and the U has to be found out from the mass flow rate. So that is the first part of the question. We'll discuss that in detail when we are trying to solve it in MATLAB. Now I'll just introduce to you the Moody's chart also. So in the Moody's chart, you can see the x-axis is having Reynolds number U d rho by mu. And on the right axis, you have the phi, which is nothing but the frictional factor, that is F dash divided by 8. Okay. And here you can see several curves. So the first curve, if you see, it is given as phi is equal to 8 by Re. Okay. So this straight curve that you see here is for the laminar region. So in the laminar region, phi is directly related to Re by like a constant 8. So it is basically phi is equal to 8 by Re. It's a straight line. Now, on the other hand, if you look at this, here you can see several lines. Why is that so? That is this region, the entire several lines that you see is for the Reynolds number, which is higher. So that you can see here in the x-axis. Here towards this region, the Reynolds number is really high. So this falls under the turbulent region. Okay. And the turbulent region, you can see different E by Ds that is given. E by D, that is actually the roughness factor basically. So the roughness you can see 0.05, you have one line. For 0.04, you have another line. And lower you can see for 0.01, you have another line. And this is for smooth pipes. So I'll just give you a thing, the hint that this will help you to solve a problem, which I'll be showing it in this session. So for smooth pipes, you can see that thing that the roughness, that is E by D ratio is almost equal to 0. Okay. So what happens is when we have a turbulent flow, the roughness factor also plays a role in determining the head loss or the friction factor. Okay. So that can be obtained from Moody's chart. So how do you read this Moody's chart? In the Moody's chart, if you know the Reynolds number, so imagine I know the Reynolds number, which is 10 raised to 5 here. Okay. And I know the roughness factor, that is 0.02. Okay. Let's take this as 0.02. So what I do is, given the Reynolds number and the roughness, it is somewhere here. And then I go horizontally, I get the phi to be equal to 0.006. Okay, so that is phi. So how is the phi f dash related to it? F dash is a frictional loss. How it is related to it? So it has to be multiplied by 8. So basically, f dash will be 0.006 multiplied by 8. That will be the frictional loss. Okay, that will be the friction factor. Sorry. Okay. So is that clear to you how to read the Moody's chart? Do anybody have a doubt? So once that is clear, first we need to identify what's the Reynolds number. So for calculating Reynolds number, you need to have the U, that is a flow rate, which has been given here. Okay, which is we in turn can find out from the mass flow rate. Next is D, the diameter of the pipe, which is already given. Density has to be found out and mu. So basically density and mu, that is viscosity and density of the fluid, has to be found out from literature or from the tables. Right now, it's just 98% sulfuric acid, so it's not very straightforward. So mm, just a second. Yeah. So basically the Reynolds, so basically this two factors here, what we have is the density and the viscosity of sulfuric acid has to be determined by the tables. And then we have the E by D. Okay, the E by D, that is the roughness factor, is also a property of the pipe, the roughness of the pipe. So basically that will be also given to you in the question, or else you'll have to take it from the literature. Now, you know that it's not every time easy to like go to the Moody's chart and keep reading the values. So there are some empirical relationship that can that can help us calculate the friction factor. So there are several empirical relationships which you can go to the recorded lectures and you'll see the several empirical relationships. But here, what we'll be looking at is a correlation. That is, the Coolbrooke correlation is for the laminar flow, F dash is equal to 64 by Re, which is pretty direct because we know phi is equal to 8 by Re and phi dash is equal to, so phi is equal to F dash by 8. Okay. So if you equate this equation, so basically, I'll just write here. So basically, phi is equal to, okay, F dash by 8. and that is equal to 8 by RE. So basically, you'll get from here that phi dash is equal to 8 multiplied by 8, that is 64 by RE. Okay, so that's the relation from the Colebrook equation. That is, the laminar region, the friction factor will be nothing but 64 divided by the Reynolds number. So that is pretty straightforward. Now going forward, now we have the turbulent region. So the turbulent region, the relationship is a little bit complicated because you have the phi dash coming in two different places. So basically, for getting this phi dash, you will have to equate this equation to 0. So then you will be getting what is the friction factor. So for calculating the friction factor, what all do you need? You need the E by D ratio, which is the roughness, which is the property of the pipe. And then we need the Reynolds number. Once you have these two quantity in this equation, only f dash is the unknown, so you can equate it to 0 and then you can get the value for it. Okay. Now coming into solving this equation. So this is where the MATLAB mainly comes in. So here it's a very pretty straightforward formula. So this you can like manually also try and find out what is the friction factor. But when you come to the turbulent region, you know that you have to solve this equation. And you also know that this equation is not pretty straightforward. It's a bit difficult when you're trying to do it manually. So for that, we'll use inbuilt MATLAB functions that can help you solve the problem. So for that, there are already several MATLAB solvers that are available. For example, if you have an equation f of x is equal to 0, okay? So before just explaining, I'll be explaining three methods. One is the Newton-Raphson method. Then I'll be explaining two inbuilt MATLAB solvers, that is fsolve and f0, okay? So these three solvers we'll be trying to discuss in this lecture, and so that it will help you to code in further sessions also. And in case you have like assignment questions from this, you can also answer them. So if you have a question like f of x is equal to 0, so that is here f of x is this. Okay. Here instead of x, you will have like f dash is the variable. Okay. If you have an equation like this, f of x is equal to 0, the first method is you try rearranging it in such a way that you get a relation that x is equal to g of x. Okay. If that is getting you confused, I'll just give you an example. If you have a question like this, 2 minus x plus ln x is equal to 0. Okay, so this is an equation. 2 minus x plus ln x is equal to 0. So this is a f of x part. Okay, now let us convert that into x is equal to g of x. So there are two ways in which you can do that. Either keep this x here. Okay, otherwise do one thing. This minus x, you can take it to the other side. Then it will become 2 plus ln x is equal to x. That is this equation. Okay, and the other one is you can take this log x to the other side. So basically what happens if you take log x to the other side and if you take the exponential of it, you'll be getting this equation. X is equal to e raised to x minus 2. So these are two ways you can do it. Okay. Now you can see there is x both on the left hand side and the right hand side. Then how do you do it? So then this will become an iterative procedure. What you do is you first get a guess. Okay. You give a guess for the first x value. Okay, give the guess for the first x value here. Then from that, you get a new x value. Again, give the new x value here. You will be getting a newer x value. You keep doing that until you will find that the x value stops changing. Okay, so that is what you meant by an iterative procedure. You start with an initial guess. Okay, with an initial guess, you get a new guess. Again, put the new guess back into the equation. You'll get a newer guess. How long do you continue it? So you continue as long as the value that you're getting from this equation stops changing. Okay, that is when you stop your calculation. So similarly, you can work with this equation also. You can start with an initial guess, and from the initial guess, you'll get a new guess. Again, put that back into the equation, you'll get a newer guess, and keep on doing it until your x value, whatever x value that you're getting from the equation, stops changing. That is when you understand that okay, the solution has reached a convergence value. And now in this question, there is again another point that has to be taken care of. This question, that is 2 minus x plus ln x equal to 0, basically has two solutions. So this blue line is a curve for that solution, and this has two solutions here. One at 0.1586, another one at 3.1462. Okay, there are two solutions for this. So depending upon what the initial guess you give, if you give an initial guess that is close to this value, it might land on this solution. If we give an initial guess that is close to this value, it might land into this solution. This is what happens and your equation has like multiple solutions. Based on the guess, which one is the nearest one, you'll possibly get that. Okay. So first, as I said, let us try to find the uh, answer using Newton-Raphson's method. So Newton-Raphson's method, you would have already seen it in your previous sessions, or maybe in maths you would have seen it. So if you have an equation like this, okay, this, just give me a second. I hope I'm audible. In case I'm not audible, please do let me know. So if you have an equation like this, that is, just give me a second. Okay. So if you have an equation, am I audible right now? Somebody can you let me know in the chat box? Yeah, okay, thank you. So here what happens is if you have an equation f of x, okay, how do you find the next x value? So basically what you do is this equation right now, you have taken f of x to be equal to 2 minus x plus ln x, okay? And then what you do is you'll have to calculate the derivative also, because basically the Newton-Raphson equation is the new x value is the first x value that you have minus the function value at this x value divided by the derivative of the function value at this x value, okay? Now this what you can do is, this is equation 2 minus x plus ln x. You take the derivative of it. So that is minus 1 plus what is the derivative of ln x? That is 1 by x. So the f dash of x is minus x plus 1 by x. 2 into this back into this equation. Okay. 2 minus x plus ln x comes here and minus 1 plus 1 by x comes here. So now you understand it's in every equation, this whole part is a function of x, basically xi. Now what you do is you start with an initial guess. Okay, put that here. You will get xi plus 1. Again, put xi plus 1 in this side of the equation. You'll get xi plus 2. And so on, you'll have to go on. Okay. So, but the highlight of this Newton-Raphson method is there is a very fastly converging method. But the problem is a good initial guess is required for this process to converge. Okay, you need to give a very good initial guess. This is applicable for all the iterative methods that works with an initial guess. It's very sensitive to the guess that you give. Next is it has quadratic range of convergence. That means the if you see like to give in simpler terms, you can see that the apart from the other methods, the quadratic rate means it will be faster converging. Next is okay. So this is you don't have to worry about what is fixed point iteration. So this is the thing requires good initial guess and it has a faster converging method. So first now let us see an example with this question. Just give me a second. I hope I'm sharing MATLAB. I hope you can see it. So the Newton-Raphson equation, okay? So first, the equation we are trying to solve is f of x is equal to 2 minus x plus ln x, okay? So in this case, we have to give an initial guess. Right now, I've given an initial guess, x0 is equal to 2. Okay. Now, since you're running it as a loop, right? You have to first give an xi value. You have to keep doing the loop. Okay. Either you can use a while loop. Then in the while loop, what the condition you give, you try to check the difference between the new x value and the old x value. And if that goes below a certain tolerance level, maybe 0.001 or something, you stop it. So that is how you use a while loop. Otherwise, you can do a for loop. In that, what you have to do is the for loop has to be run up to like a sufficiently amount of number of times. Okay. So here I'm running up to 50 times. And also, I'm giving a tolerance of 1e raised to minus 4. Tolerance is the difference between the new x value and the old x value. Okay. Now I initialize x is equal to x0. I also initialize a new variable x old equal to x0. Now I run the for loop here. So we run the for loop here, you will see I is running from 1 to max iter. That is, I is running from 1 to 50 times. And the function value is nothing but f is equal to 2 minus log x. Okay. Here x takes the x0 value. First value it takes is 2. Okay. Now f is equal to 2 minus x plus log x. And df is nothing but minus 1 plus 1 by x. Okay. Now what will be the new x value? The new x value will be x is f divided by df. Basically, the function divided by the derivative of it. So you'll get the new x value. Now we can calculate the error. What is the error value? Error is the difference between the new x value that you obtained here and the old x value, which was initialized earlier. Okay, x minus x old. And after calculating the error, what you do, the x old one, okay, now you replace that with the new x value here. Okay, so that this can be iteratively continued. Now, in the for loop, we also give a condition that if the error goes below the tolerance, that is, if it is below difference between the new x value and the old x value, if it is less than 1 e raised to minus 4, then I break. Break means I completely come out of this loop. Okay. Then whatever the x value I have is the final x value that I'll take. Okay. Let me just comment this off. Okay. So now let me just run and show you what this value gives. Okay. Remember my x0, my initial guess was 2. Okay. Now I'll run this. And let me just type the final x value here. Okay. Clear. CLC. And I'm again running this. You will see when I give x is equal to 2, my final x value that I get is 3.1462. If you remember, that is our second solution that we had. For example, if you look at here, just give me a second. Am I audible? Yeah, I hope I'm audible. Okay, so that is the second x value that we have got here. Second solution value, that is 3.1462. Now let us give a guess that is closer to this value, that is 0.1586. Okay, earlier guess was 2, initial guess was 2. Now I'm changing and giving the initial guess. So let the guess be equal to 1. Okay, let's see what happens. Again, running, we'll get. Okay, when you gave 1, it gave an error. Why? Do you know why? Because if you look at the equation here, okay, so if you look at the equation here, when you give 1, what happens? So a derivative become minus 1 plus 1 by 1. So that is 0. Basically, derivative became 0. That is, you're dividing some equation by 0. Okay, that is not right. So what happens is you don't get an answer for that. Okay. So let me give a different initial guess that makes some physical sense. Okay. Let me give like 0.5. Yeah. Again, run this. Clear CLC. Running. Okay, again, I'm getting the first value, basically 3.1462. And there's an imaginary part, which is almost 0. So let me give something like minus 1. Let's see what will happen then. Again, I'm getting this value. Let me give 0. Okay, that is not applicable because you have like log 0 that you don't have. Okay, again, giving minus 5. CLC. Okay, so here in this question, whatever initial guess you gave, that is giving you the 3.1462 itself. Now let me give something that is very close to 1.5 something. I don't know whether you land up there. Yeah. And I gave very, very close guess to 0.15, then it landed in 0.1586. So this method, what happens is if you give the initial guess, depending on the initial guesses, you can either get the first solution or the second solution. Okay. It can work either way. Either you might land up here for 0.1586, or else you'll get the other solution that is 3.1462. Either of them is possible. So that is about the Newton-Raphson method. It is a very fast converging method. The other only part is you have to write a code for it. Okay, that is not an inbuilt MATLAB function, so you'll have to write a code for it. Now let us look into the two inbuilt functions. And let's not forget why are we doing this? Because we want to solve this equation. Okay. So given, if you imagine that you have the E by D ratio, that is the roughness factor given to you and the Reynolds number given to you, you should be able to solve this equation so that you get the friction factor F dash. Okay, that's what we are aiming at. Right now, we saw one method, that is a Newton-Raphson method. Now, the next part is we'll see the other two inbuilt MATLAB solvers. Okay, basically, the first one that we'll be seeing is FSolve. Okay, FSolve is the one that has been used in the recorded lectures. And apart from this, we'll try to do one more solver, which is equal to F0. Okay, now next is FSolve. Basically, it's a MATLAB inbuilt function. So it solves nonlinear algebraic equation. Okay, the question that we have right now, if you remember, if you go back, you'll understand that this is a nonlinear algebraic equation. Okay, This is a nonlinear function. So this f-solve exactly does that. It solves nonlinear algebraic equation. But there is a certain way you should use this. There is a certain syntax in which you should be using this function. How is the syntax working? So xsolve is equal to fsolve. So this is a keyword that you use, a function name. And then you'll have to write at the rate x. Okay, at the rate x means you're telling the solver you have to solve for this variable. Okay, you have to solve for this x variable here. So in our case, it will be basically f dash. You have to solve for f dash. Then you have a function name. Basically, in this function, you will save the solve equation that you have to solve. And then you give an initial guess. Okay, x0 is your initial guess. So what you get as output, xsolve that you get is a resulting solution. Funname is a function file that we provide to calculate f of x. That you'll understand. We'll solve an example, then we'll understand. Then x0 is the initial guess. Remember that x0 should be as the same dimension as that of the x. Okay. So basically, you can use to solve this if there are two variables also. Right now in our equation, we only have one variable, which is f dash. But this can be extended to multiple dimensions also. So, but imagine that, but understand that you have to give a initial guess according. So now let us go to MATLAB and try to solve a question. Let me just clear this. I hope I'm sharing MATLAB. In case it's not visible, please do let me know. Yeah, okay. Now trying to solve using fsolve. So this is basically the function that I have. So this is the syntax. Okay, xsolve gives us. I'm trying to solve the same problem. The problem that we solved earlier is f of x is equal to 2 minus x plus ln x. So here we are trying to do the same problem itself. So what we have is this is the syntax that we have. Xsolve will save the final answer, and fsolve is the function name. And then you're telling that the variable that we have is x. Okay, this is the variable that we have is x. Let me just add this here. Okay, what we're trying to solve is this. So the variable that we have is x, and now the function has been saved here, fun for bisect, and x is an input, and the initial guess that I gave is 2. Now let me see what is this fun for bisect. Basically, fun for bisect, what it does is it takes the input x, okay, and it calculates this equation 2 minus x plus log x, and the final value will be in fval, which will be given as an output. So this is how you should write the function. Okay. Basically, fun for bisect means it will take an input x, okay, and it will convert the equation that you have to equate it to 0 and give the value for that fval. Okay. So that's how this function works. And then you have to give an initial guess that is 2. Now let us try to solve this. You have to just run this command here. Either you can put it in a script like this and run, or else you can just copy this command and you can run it here also. Okay, let me just run this. See, this is how you get the answer. So you'll get that the MATLAB will tell you the equation is solved. Okay. And fsolve, why did it complete? It completed because the vector of function value is near 0. Basically, this equation has got equated to 0. And it's between the function tolerance. That is, since MATLAB is a software, it has like a tolerance level and everything, so that the inbuilt command functions can converge. Okay. And if you can see here, you can see the stopping criteria details here. If you just click here, you'll see the sum of squared function value should be this value less than this one, and function tolerance between should be this e raised to minus 3, and optimality tolerance. So these are some technical terms. You can go and check it if you're interested in it. Now the final answer that you get is xsolve is equal to 3.1462. Okay. Now the same thing, let me try giving a different initial guess. I gave 2 initially. Now I'm trying with 0.5. I'm getting the first solution, that is 0.1586. Okay, I'm getting the first solution. Let me give another guess. Okay, that is 5 here. I'm getting the second solution, that is 3.1462. Again, the equation is solved. Okay, now let me give a not feasible value, because if I give 1, you saw that in Newton-Raphson, it doesn't give you the answer, right? So let me try for this one also. Here it gives, this is not feasible. This initial guess is not feasible. So you get no solution found. fsolve stopped because problem appears in regular as like there are reasons for that. So you don't have a solution. So you can take this value basically. Okay. This value is wrong. You get the initial guess itself as answer because no solution was found. Okay. Is this fsolve example clear? Do you have any questions? If you have any questions, please ask right now because you have like assignments to solve based on this. Okay. So since you don't have any questions, let me just move forward. So that's it with Epsol. So in Epsol, what you need is you need to have a function, okay? And you need to start with an initial guess. So now here, let me just compare this. Epsilon and Newton-Raphson method cannot solve with an initial get, that is a local minima or local maximum. Okay. Basically, if you see x is equal to 1 was a local maxima here, that is the maximum of this curve. You can start with like such infeasible points. Okay. Initial guess, which is to the left of the maxima. Okay, left of the maxima here, that is left to this side, gave you the first solution. And the initial guess, which is right to the maxima, gave you the second solution basically. Okay. So if you give one solution that is 0, close to 0.1, you will land here. But if you give some value to the other side that is greater than 1, you will land up in the second solution that is 3.1462. So this we saw as initial guess. When we give 0.5, we got the value 0.1586 from the epsilon. When you give 2, you gave the second solution that is 3.1462. And when you gave 5, we also got the second solution which is 3.1462. Okay. So this is how we use the epsilon solver. Any doubts? Okay. If not, let me explain the F0 also. F0 also solves non-linear algebraic equation, but there is a difference in how you give the input to it. Okay. This uses a mathematical method which is called as bracketing method. So bracketing method means the traditional bracketing method is like this. You give an upper limit and lower limit for the actual value. Okay. Imagine my actual solution. Okay. Here in this case, actual solution is 0.1586. So I'm giving a bracket. Okay, bracket for the code to find. I'm telling that, okay, my value is between 0 and 1. That is my bracket that I give. Now, what happens is in the bracket, it will try to find a solution. Basically, it usually is the midpoint of the bracket. And then what happens is it checks the value at the midpoint and then it lowers the bracket. So basically, the bracketing method is like this. Let me just show you graphically. So in the bracketing method is imagine you have got a bracket like this. Okay. This value is 0 here and this value is 1 here. Okay. Now you take a value here in between. Usually we take between and we calculate what is the value here. Okay. Basically in bracketing method, the sign of the function. Okay. If you're taking two functions, if you're taking 2 points, okay. At one point, the value has to be positive and the other point, the value that is basically f of x has to be negative. Okay. Now you find a middle point. You calculate what is the function. You check what is the sign of this function. If it is positive, what you do is you discard this positive value and take this as the bracket. Okay. If the value is negative, you basically discard this and you take this as the bracket. Okay. Now once you've got, imagine that this is the final bracket I got. So here it is positive and here it is negative. Okay. Always on the brackets, the two side values. Okay. The bracketing angles that you have, the value should be of opposite signs. So once you've got that, what you have to do is you have to again calculate the midpoint of it. Okay. Again, see what is the sign of this value. Imagine that this is negative. Then you discard this end and you make this as a bracket. Okay. Again, plus and minus. Again, you take the midpoint. Okay. Imagine that this was positive. Okay. And this is as usual negative. So you discard this one. Okay. Discard this one. And you take this as the bracket. Okay. And so on, so on. This bracket, it was initially very large. It is reducing its size and finally it will converge into a single value. This will converge like this. And finally it will land up on a single value. So that's how this bracketing method works. So F0 uses the same theory here. So let me just clear it for you. So here what happens is F0 has almost the same syntax. So XOR is the final solution that you have. F0 is the MATLAB function's name. You are telling that MATLAB function, okay, the variable that we are trying to solve for is X here. And then you have a function name. And then you have an initial guess. And the initial guess is for the bracket. Okay. That is what you have to keep in mind. So XOR is the resulting solution. Fun name is a function file that we provide to calculate f of x. And x0 is basically the bracket. So that has an xl, that is a lower limit of x, and xu, which is an upper limit of x. This is the vector for initial guesses. Okay. So let me try to solve this question. The same question, we'll try to solve it for f0. We'll try to solve it for x0. So here the syntax is pretty similar. F0 at the and you're telling the MATLAB, okay, the function, the variable you have to try to solve for is x, and the function name is fun for bisect. Okay, the same function here, what we used here, the fun for bisect. Basically, you take an x value and it compute 2 minus x plus log x. Okay, and the interval that I'm giving is 1 to 4. So basically, I should be getting the second guess. Okay, that is 0.31. Basically, that is the value that I'm looking for. So let me just run this. Either you can run it here. Okay, I'll just run it here. And we got the second solution, that is 3.1462. Okay, now the same thing, I'm giving a different guess. Let me give 0 to 1. What will happen? Let's see. Let me clear it. VLC. Running this. Okay, this is not feasible at the endpoints. So let me give a different initial guess. Maybe 0, 1, and minus 1. And let's see what happens. Again, this is not feasible. So the thing is, as I said, the signs has to be opposite. Okay. So let me just go see the graph once. It was given 1 and 4. 1 is positive and 4 is negative. Okay. So for here, 1, the value is positive here. And for 4, the value is negative here. So for getting this, what I give is, I have to give a value which is not 0 for 0 because it's infinity. Okay. So I'll give something 0.5 and 0.05. Let me see that. Is the value correct? Yeah. 0.5 is here and 0.05. Let me try do that. 0.05 and zero point 0.5. Clear. CNC. Yeah. Now we've got the second solution. Okay. That is 0.1586. So this you have to keep in mind the signs of the function. Okay. So basically, when I gave 0 as an initial get, at 0, the value is like infinity. So basically, you can't try to use that. But wherever the function value is proper, and it has to be of opposite signs. Okay. So opposite signs means it has to be, one has to be positive. One of the limit has to be positive and the other limit has to be negative. Okay. In that case, you can use fun for bias. In that case, you can use F0. So basically, if we have a nonlinear algebraic equation to solve, there are several methods. Here we discuss 3 methods. One is the Newton-Raphson's method. Let me just take you back. One is the Newton-Raphson's method. And the second one is the MATLAB function F-solve. Here you have to give an initial guess. In Newton-Raphson also you have to give an initial guess. And another one is F0. Here instead of initial guess, you can give an interval. So whenever you have an interval that is mentioned, you can be using F0. If you have an initial guess that has been provided to you in the question, you can use F-solve. Any question? Okay. There are no questions. So let us go to the problem that we had. That is, we need to solve this equation to get the f dash. That is, instead of Moody's chart, we are using this correlation. Okay. So now we'll go to the first part of the question. Just give me a second. Clear. CLC. Okay, so these are the things that is given to us. The first is G. The flow rate is given to us is 1.5 kilogram per second. And the acceleration due to gravity G is equal to 9.8 per meter per second square. And D is the diameter of the pipe that is given as 0.127. Okay. And E by D ratio, imagine that it is given to you in the questions. Here it was not found. Then you'll have to find it from literature. So for time being, we'll fix E by D ratio to be equal to 0.05, which is the roughness factor. And the effective length of the pipe is 375 meters. And rho, that is the density of 98% sulfuric acid from literature, it can be taken as 1830 kilogram per meter cube. Just make sure that everything right now we have converted into SI units. So whatever value you take from the literature also has to be in the SI units. Okay. Next is we know we need to find the u, that is the velocity. So as I told you here, the mass flow rate was given to you. From the mass flow rate, you can find the velocity. How do you do that? So first we have to find the area. Okay, the area of cross section. So basically, area of cross section is pi r square. Here what we have is the density. What we have is the diameter. So what we do is pi d square by 4. That is basically the area of cross section. So that is 1 by 4 pi d square. D is given to us already. So here you get the total area, the cross-sectional area. Once you have the cross-sectional area, the velocity is nothing but the mass flow rate divided by A multiplied by the density. Okay. Just keep this in mind. You would have solved questions like this. Once you have the mass flow rate, you have to just divide it by the area and the density. Then you will get the velocity. Okay. So the velocity can be obtained as G divided by A multiplied by rho. Now the mu, that is the mu is the viscosity of sulfuric acid, also has to be given to you, or it can be taken from literature. So this also has to be in SI unit, that is in Pascal second. So the unit is 26.7 e raised to minus 3. Now first we have to calculate whether this region falls in the laminar region or the turbulent region. So for that, what do? You first calculate the Reynolds number. Reynolds number is nothing but du rho divided by mu. So Reynolds number can be found from here. Now, if the Reynolds number is between 0 to 2200, okay, you have to find using the laminar flow regions formula. If it is beyond 2200, you have to find using the turbulent regions formula. Okay. So now we'll come to that region part. So let us see right now what is the region what we are looking for right now. Okay, just a second. Yeah. So before that, let us see what is the functions laminar and turbulent. Uh, so yeah, this is the laminar function that is given the Reynolds number. It should output the friction factor for you. So laminar means it will take the Reynolds number as input, and the friction factor is nothing but 64 divided by Re. This is a very straightforward formula. So you will get the friction factor for the laminar region. Now coming into the turbulent region, this is where you have to use the F solve or F0 or whatever solvers we have. Here what happens is, you saw the Coulomb equation, right? So in the Coulomb equation, what are the inputs that you should give to get the friction factor? In the Coulomb equation, you need to give E by D ratio, that is a roughness factor, and Reynolds number. Okay. Then the only unknown is F dash. So that should be the two inputs, that is E by D ratio and the friction factor. Sorry, E by D ratio and the Reynolds number. So you give Reynolds number and E by D ratio. What does it do? This is the function that we are looking for. This is basically the Coulomb equation. That is 1 divided by root of f, that is f raised to 0.5, plus 2 times log 10. Okay, remember that in the Coulomb equation, that is known as the natural logarithm, that is log to the base 10. So now 2 times log 10, E by D ratio divided by 3.7 plus 2.51 divided by Re, and again Re multiplied by root f. So this is the equation that we are trying to solve for. Okay, actually this was unnecessary here because, okay, and this is how you do the F solve syntax. Okay. So that is F solve. What the variable you're trying to solve is F. Okay. Basically, F is the variable. And again, you've repeated the formula here. Okay. This was basically unnecessary here. So we can just comment it off here, this part. Okay, you don't have to repeat it. Either you type here for the whole equation, you type this function, this func name, or else you can directly type it like this, just like we did for 2 minus ln x, 2 minus x plus log x. Okay, the previous example. And then you give an initial guess for the friction factor. Here I'm giving 0.150. Now what happens? Fsolve will solve it and it will give the friction factor for me. Okay, Fsolve, what it does, if you give an equation, it will equate it to 0 and find the unknown quantity for you. Here E by D is known to you, Re is known to you, so the only unknown is F. So that is what we are trying to solve here. We are trying to solve for F variable. So now we will get the final answer here. Given the initial guess 0.150. Okay, so that's it. Now, given the friction factor, now we have to find the head loss. So the head loss expression we already know. Head loss is F multiplied by L by D. L is already given to you, 375. D is also given to you, the diameter. Yeah, 0.127. U square, U we calculated from the flow rate. Okay. And then divided by 2G. And now finally you'll have the head loss factor. So let me first see what is the Reynolds number. I'll just print this Reynolds number also so that we have an idea which region it falls. Okay. Now let me run this for you. Okay. The Reynolds number is 5632308. Obviously, it falls in the laminar region. Okay. And the laminar region, okay, I'll just, okay, the semicolon I've removed so that I want it to be printed here. Let me just run this again. See, for the Reynolds number is 5632308. As a friction factor that is obtained, that is 64 by RE. That is the formula that we used. We got 0.1136. That is a friction factor. And for this friction factor, the head loss is 0.071599. Is this clear? Any questions? Okay. I hope this part is clear. Now let us go to the second part of the question. Okay, now we know how to use F-solve. Now going to the second part of the question, which was examine the effect of Reynolds number on the frictional head losses when RE is in the laminar region, that is 50 to 1500, and RE is between 5000 to 25. Let us try to find that. Just give me a second. Yeah, I hope I'm audible. Okay. Now what you have to do is the basic idea is here what we had is we had a particular Reynolds number that is given. Okay. And for that we found the friction factor. Now we have a range of Reynolds number. So what you do, you keep changing the Reynolds number and you repeat the same procedure that we did. How did we find the head loss? The same thing, you keep doing it again and again for different Reynolds number. Okay. That can be easily done if you're trying to use a loop. So we'll see that part of the question. That is second part. Okay. So everything remains the same. The D, G, L, all the variables remains the same. The highlight is here. Okay. So here I'm fixing a Reynolds number RE. RE is ranging from 500 to 1500. I remember we had discussed about this colon operator. What I'm doing is I'm creating a range of values from 500 to 1500 with the difference of 100. The step size that I'm taking is 100. So that is my first vector, RE1 values. Next is my second vector for the turbulent region. That is RE2 ranges from 5000 to 25,000. The difference is of 1000. You can play around with the difference. Okay, that's completely fine. Okay, and then what you do is you put this in a loop. What do you do? What do you put in a loop? This portion. Okay, this portion where you calculated the friction factor, that you put it in a loop, and where you can calculate the head loss, that also you put it in that loop. Okay. So basically, what do you do? When RE is between 1 to in the laminar region, okay, when RE is in the 1 to the last value of the laminar region, you calculate the friction factor using this function. Okay, laminar RE, the first index. Okay, this for loop goes from first RE to the last RE. Okay, it first goes from 500, then it goes to 600, and so on till 1500. So it calculates the friction factor from laminar, this function. Once the friction factor has been calculated, you find the U value. U value, why we'll have to find the U value? In the previous case, we had a fixed U. The Reynolds number is just a single value here. Here, you know, the Reynolds number keeps changing. So for this Reynolds number, what is a U? Everything is known. Reynolds number is given. Mu is given. Rho and D, everything is known to you. So you will get it from here. Now the head loss is nothing but F is given to you. You got from here this equation. L and D was given to you in the question. You found out from this equation for Reynolds number and then divided by 2G. You will get the head loss. So first you get it for 500, RE equal to 500, then you get for RE equal to 600, RE equal to 700 and so on. Okay. To save the value, okay, to save the values of RE, you know, it is a vector, right? So to save the head loss also as a vector, I'm saving it here. So RE in the bracket, when I give I, what happens? This, when I equal to 1, you get the first value. When I equal to 2, basically I will be there as long as the RE is there. Okay, 1 to length of RE. So that's how you get a vector. Any doubts in this? Should I explain this again? Yeah, okay. Now, as you've understood that, now that's how you get the RE value. Then you plot Reynolds number versus the head loss. It's a line plot. Basically, the X label, I'm adding it as Reynolds number, and the Y label is the head loss, which is in meters. Now repeat the same thing for the turbulent region. Again, the turbulent value goes from 1 to length of RE2, and you use the turbulent function. Okay, what all input do you give? You give the Reynolds number. Okay, you give the Reynolds number and the E by D ratio. E by D ratio is fixed here. Now you calculate the U exactly how we did for the laminar region. Okay, and then you find the head loss here, HF2. You keep repeating it for values ranging from 5,000 to 25,000. Okay, once that has been done, again you will get a vector for it. And then we plot it, RE versus HF2. Is that clear? You repeat the same command by putting it in a for loop. That's what we did here. Now, once that has been understood, let me just plot this. I'll run this for you. This is taking a bit time. Why? Because every time for the turbulent region, this equation has to be solved, right? So it will take a little bit of time. Mm, just a second. Let me just run this again. I think I missed something. So this was a figure one that is basically for the first equation. That is the laminar region. Here you can see Reynolds number RE1 is here. 500, 600, 700, 800. And similarly, the head loss is also like this. Okay. So if you see the length of the function here, you will see RE is having 11 data points. Similarly, correspondingly, HF also has 11 data. RE2, that is for laminar region, you have 21 data points. And similarly, head loss will have also 21 data points. So this is the behavior that you get. This is for the laminar region. You'll get a straight line like this. Let me just close it once. And this is for the turbulent region. You'll get a little bit of a curve. Okay, this is expected because if you look at the Moody's chart, in that the laminar region was a straight line. And here you'll get a curved structure, and the curved is a very small curve because you have done it for a very small range of Reynolds number. Okay, if you do it for a large range of Reynolds number, you'll be getting the behavior like that you observed in the Moody chart. Any doubts in this? Okay. If not, let us go to the next session of the question. That is generate your own Moody's chart. Okay. So in the Moody's chart, you remember that given the what all details you need the Reynolds, and that is for the turbulent region. Okay. In the turbulent region, what all you need? In the turbulent region, right now we created one graph. Okay. But the highlight of that graph is the roughness factor was a constant. So basically, we have generated only one line among the series of lines. Now what you have to do is you have to keep changing the roughness value so that you get a different set of lines here, all set of lines. Okay. How do you do that? That you can add inside a for loop, you can add an extra loop. So that is E by D values can be varied. So that's how you do it. So let me just go to the question. Fast. Yeah. I'm just quickly explaining it because this has been already discussed in the recorded lecture. So in case you have any doubt, you can pause me and ask. Okay. Now E by D, I'm ranging from different values, that is 0 to 0.0008, and that has been varied, E by D ratio. Okay, just a second. Here, CLC, close out CLC. Okay, so now you have a series of E by D ratio. Okay, that is ranging from 0 to 0.008. Then it goes from 0.001 to 0.008. This can be written. Okay, the different range of REs from 0 to 0.5. You can divide it however you want. And the Reynolds number also I'm dividing in the turbulent region. I'm having a very fine refinement from 5,000 to 10,000. It goes up to e raised to 6. Okay, there's a large region of Reynolds number for the turbulent part. Now what I'm doing is I'm defining some phi's. Phi's basically the friction factor. I'm trying to save it here. Okay, as zeros. Why phi is because in the Moody's chart the y-axis was phi, not the friction factor. Okay, so here I'm trying to find phi's, not the we can find the friction factor. From that it has to be converted into phi's. So first, the part is this like you use two nested for loops. One is if it has to run from different E by D values. And instead the E by D values, you have a different loop that is running for across for all Reynolds number. So how does it work? So basically, for 0 E by D, you do this different range of Reynolds number from 5,000 to 1 raised to that is E raised to 6. Then you go to the next E by D, that is 0.002. For that also, you do the entire range of Reynolds number. So that is for the one Reynolds E by D, you do all the Reynolds number and you keep changing E by D. Okay. That's how you get the different lines. That is different. If you remember in Moody's chart, each line E by D was a constant, right? So again, the formula, we use this formula. Remember, RE is also a vector, E by D is also a vector. So it has to be, index has to be properly given so that you get a specific value from the vector. Now you get the F from here, and that has to be converted into phi. How do you convert into phi? That is, you have to just divide it by 8. You get the phi value. And that also, it has to be for a particular E by D value, the index is corresponding to I. And the a particular R value, the index is J here. So phi ij will be this value, right? And then this is a plot. If you remember, the plot that we had was a log-log plot. Okay, that is why. So that is both x-axis and y-axis was the logarithmic scale. So in MATLAB to plot in log-log plot, and the syntax remains the same, just that instead of plot command, you have to use log-log. So basically, it is log-log re phi 1 to end, then all the values has to be plotted. And this is x label, y label. Then I am adding text here. Okay, x coordinate and y coordinate texts, and I'm adding one line that is e smooth pi is an e by d, basically whatever is there in the Moody's chart. So let me run this for you. So basically this is how you got. This is, remember, this is a log-log plot. Okay, so very small value, that is for smooth pipes. When e by d is equal to 0, you get a straight line here. So this is a straight line that you get. Okay, and then this is for different e by d's. For e by d equal to 0.5, this is a red line that you see. You get different lines like this. Okay, this is a nested for loop. The outer loop is for a E by D value, and for each E by D value, you change the range of the Reynolds number. And you get the friction factor. From the friction factor, you get the phi. And you plot the phi versus the Reynolds number for different range of different E by D in a log-log plot. Is this clear? Any doubts? Yeah, the log-log plot syntax is like this. Yeah, you can go to MATLAB and type help log-log plot so that you'll get an idea of it. Clear CLC help log-log. Sorry, there is no space. Yeah, it's same as plot function, except, hello? Yeah, do you have a question? Okay. So in log-log plot, what will be happening is both the x and y axis will be in the logarithmic scale. It's same as a plot function. In case you have doubt, you can ask me. Okay. Once you've understood that, then we'll go to the problem solving session. Okay. I hope you understood the three functions that we discussed. One is for Newton-Raphson, other one is F0, and the other one is F-solve. Okay, three of them we did. Newton-Raphson is having a faster conversion, but it's not an inbuilt MATLAB function. So for that, we'll have to write a code. F-solve is for solving nonlinear algebraic equation given an initial guess. Okay, and the second one, F0, is also for solving nonlinear algebraic equation, but in that case, you have to give a bracket. You have to give a upper limit and lower limit for the solution. Now we'll go on to the next session. That is, I'll give you questions and I'll give you some time, 3-4 minutes or something. And then if you have doubts or something, you can pause me and then we'll discuss the answers. If you have got the answers, please do put it in the chat box. Okay. This is the first question that you have. Please try to solve the questions right now itself because this will help you solve your assignment questions. So the question is calculate the lower limit of friction factor for laminar flow. Okay, I'll give you 3-4 minutes and then we'll discuss the answer. Once you've got the answer, please put it in the chat box. 2 more minutes and then we'll discuss the answer. Once you've got the answer, please put it in the chat box. Calculate the lower limit for the friction factor for laminar flow. So for that, what do you know? You know the relationship between friction factor and the Reynolds number in the laminar flow region. And you know it's inversely proportional, right? So once it's inversely proportional, what you have to do is you have to give the upper limit for laminar flow so that you get the lower limit for friction factor. So it's because it's inversely proportional. That's a hint that you have. 1 or 2 minutes and then we'll discuss. Somebody has given me the answer. Yeah, A. Just put in the chat box, okay? Don't annotate it in the PPT because, yeah. Yeah, thanks. I got the answer. We'll discuss a solution, okay? So basically, the question is lower limit of the laminar flow. Just a second. So you have this, am I sharing the MATLAB? Yes, I'm sharing it. So you can directly use this function if you have to, CLC. So you know the Reynolds number, let us give like for 2200. Okay. Yeah, the value that you get is 0.0291. Is that in the range? Yeah. Sorry, I think I gave just a second. Yeah, so the Reynolds number what we have is 0.029. Yeah, right. No, please don't stop annotating it. You can just put it in the chat box. I'm reading the chat, okay? Just a second. Yeah. So the thing is, Reynolds number, what we know is upper limit is 2200. Okay, and the friction factor, you know that is 64 divided by the Reynolds number. So we give the upper limit of the Reynolds number so that we get the lower limit of the friction factor because it's inversely proportional. So you get 64 divided by 2 to 0, that is 0.029. Okay, that is approximately equal to 0.03. So the answer is B. So the second one. Okay, B is the answer. So the upper limit of laminar flow friction factor is 0.03. I hope this is clear. Now moving on to the next question. Yeah, got a yeah, answer is B. Yes, you're right. Ramesh Chandra. Yeah, answer is right. Next is the friction factor is inversely proportional to Reynolds number for turbulent flow. Yes or no? It's a quick question. You can give it the answer in the chat box. If you remember, just try to recollect the relationship that we have. Basically, we are trying to recall the Coolbrooke equation for a friction factor. And in turbulent region, you know how the equation looks like, right? So the answer is no. According to Coolbrooke equation, the friction factor is not inversely proportional to Reynolds number. If you want, we'll just go back. Sorry. Yeah. Here you can see both Reynolds number and friction factor both are in the denominator. So it's not inversely proportional. Okay. And the relationship is like a little bit complicated in Coolbrooke equation, so you can't say it is right. Yeah. Now, yeah, answer is no. Right. Now the next question. This you can take a little bit of time. It's very simple. If you have MATLAB, try to solve this in MATLAB. Or else take a pen and paper and try to write at least the basic lines of code. Okay. Fsolve, we know how to use it. We have discussed that in the today's session and also in the recording. We have the Fsolve being solved. But here the changes here we have two equations and two unknowns. Okay, just think a bit. If you have MATLAB, you can use the help command in MATLAB to figure out how to use Fsolve once again. So these are the equations, and I'll give you like 4 or 5 minutes, and then we'll discuss the answer. Okay, we need to find both. There are two unknowns, two equations. We need to find both x and y. And for x, you have the initial guess as 4, and y, you have the initial guess as 8. Okay, I'll give you 4 or 5 minutes. Even if you don't figure out the answer, it's fine. We'll discuss it. Okay, I just want to give you some time so that you can try to write the lines of code because just giving me the answer then and there will not help you. Okay, just think for a bit, and if you have MATLAB, try to solve it, and if you have the answer, just let me know through the chat box. So how do we solve this question? So let me just go to the solution here. So the basic idea is in Epsol, we have to write an equation. We have to write a function that can find you both this equation. Okay. So we'll try to see the solution. So this is the first line that we have. X0, basically you will have the initial guess for both X and Y. So for the X initial guess is 4, Y initial guess is 8. Make this a column vector. And this is how we use it, xsolve. The function name is fsolve that we use, and we are solving it for this, both x4 and 8. Okay. 4 and 8 means it will be basically the input to this. That you'll understand later what x means here. The function that both the equations are there is called as 1, 3. And this is the initial guess, basically the column vector, 4 and 8. And then you'll get the answer when you run this. But what is fun 3? So that is a important part. Fun 3 means fun 3 takes an input x. Okay. And there is a, if you see, have you seen the equation, there is like a constant given d. There is a constant given d, and d is equal to 3. This is a constant value, and rest of them are like variables. So d equal to 3. Let's code that first. D equal to 3. And in that, x has two values. The first value, basically, x is the vector of two values. Okay. The first value of x is nothing but the small letter x. And the second value of x is nothing but the small letter y. And then you write the equation. The first equation is, so basically equations also forms a column vector. Okay. It has like a single column and two rows. The first equation will be d 12 minus y minus 80 xy divided by 50 plus y. Basically the first equation. And the second row, you will enter the second equation, that is 60d 1.5 minus 60y divided by 50 plus y. Basically, the equation that is given to you. And this function, okay? Remember earlier the initial guess that we gave here, this also was a column vector, 4, 8. Similarly, the function that we gave here, fun3, should also output a column vector. In that, the column is a single row and two rows. In the first row, we have the first equation, and in the second row, you have the second equation. Okay. So this you give two equations and that will be the output here. Okay. That is what we are using here in fun3. And basically you run this simply. So we'll see what the solution is. So basically both the equation has been solved. So you'll get equation solved. It got completed and the value that you get is, remember the first value that you gave was for x. So your x is 6.1977 and the second value is y and the y is 2.9101. Okay, this is how you solve. So similarly, you can solve like multiple equations in Fsolve. Is this clear? Any doubts? Okay, I hope you have understood how to use Fsolve, the syntax and everything. Just that you can stack your initial guesses as a column and the equations also can be stacked together in a column vector. And you can use the same syntax as we did before using Fsolve. Okay. In case you want, you can just take a screenshot of this. Yeah. Now going back to the next question, I hope you understood. In case you didn't understand, please stop me and you can maybe unmute yourself and ask a question or else put it in the chat box. Yeah, so this is the next question. Determine the friction factor for a pipe with Reynolds number and relative roughness given this. Okay, I'll give you like 2-3 minutes and then we'll discuss the answer. If you have answer, please put it in the chat box. Yeah, I've got an answer here. So let us discuss. So the Reynolds number is 50,000 and the relative roughness is 0.001. Okay, what we need to find is the friction factor. So the answer is basically B. Yes, what you got is right. So the friction factor, actual friction factor is 0.0240. If you have a doubt, we'll use Matlab also. 50,000 and 0.001, right? So yeah, we can use the function that we've already written. That is the turbulent one. Where is it? Just give me a second. Yeah, this equation. You know the input that you have to give is Reynolds number and E by D ratio, right? So Reynolds number is 50,000, okay? And E by D ratio is 0.001, right? So the final answer that you get is 0.0240. Is it the same thing? Yeah, 0.0240. That comes in the B part. That is 0.02 to 0.04. Okay, yeah, got the answer right. And the next question, again, find the zero of a nonlinear function. The initial guess is x is equal to -1 using f0 in the MATLAB. And this is the equation x cube minus x sine x plus 1 equal to 0. Again, I'll give you 2-3 minutes. Yeah, Ramesh, you can just write in the chat box, okay? You don't have to annotate in the because other people will also find it difficult to answer. Okay, just write it in the chat box. I'll read it. Please write it in the chat box. Yeah. So let's discuss this answer. We'll solve it in MATLAB. Okay. And the initial guess is what X, sorry. Uh, I hope you can see the MATLAB portion. So initial guess is X is equal to -1, right? So let me just try to do that. Clear CLC. Just a second. Let me just give me a second. I'll figure out the answer. Okay, since the answer is not here, let me just try to code that. Okay. So you have the F0 function. We have an example here. F solved example is here. Okay. Similarly, we'll try to do this. What's the equation that we have? The initial guess is -1. And the equation that we have to solve for is x cube x minus x sin x plus 1, right? X cube minus x sin x plus 1. So here, what do? You write x cube uh, minus x multiplied by sine x, right? We have to put it in a bracket. So sine spelling, yeah. And what was it? Plus 1, if I'm not wrong. We'll confirm it again. X cube minus x sin x plus 1. Okay. Yeah. The final answer that you get is minus 0.7725. Is everybody getting the same answer? Okay, I hope you guys are getting the same answer. If you have any doubts, please do ask me. Okay, then let us go to the next problem. Determine the friction factor of a smooth pipe with Reynolds number is equal to, yeah, 1 lakh. So I'll give you 2-3 minutes. You can just put the answer in the chat box. Okay, we have done problem similar to this. Yeah, do you have an answer? If there is no question, please unmute yourself. Any answers? So this is the answer. From the Moody's chart, you know the line for the smooth pipe. Okay. So thereby you can directly read it. So otherwise, what you do is you can use the Coolbrook relation. In the Coolbrook relation, you know the E by D ratio. That is a roughness factor. For a smooth pipe, it is zero. Okay. So directly in that equation, you can put zero. This is the what you say, the equation for the turbulent region. Okay. So here you can use the same equation here. The friction E by D is equal to 0 and it is 1 lakh. Okay, let us try to keep that in MATLAB. You know the turbulent formula, right? Just give me a second. Yeah, this was it. Yeah. And you'll give E by D equal to 0. And Reynolds number that was 1000000. Right? Yeah. You get 0.0180. Let's see what is the answer. Yeah, you get 0.0180, which is the answer is B. It falls between 0.01 to 0.03 range. Any doubts? Yeah. If not, let us go to the next question. Find using F0 the answer for this function between the interval 0, 1. I hope you know the syntax of this question. A syntax of this using F0. So I'll give you 2-3 minutes and then we'll discuss the answer. Let's try to figure the answer of. Okay. So the equation is e raised to minus x sine 2x minus 0.5. Okay. And if you remember, this equation is not directly equal to 0. Okay. So first you'll have to convert this equation into that. It equates to 0. Well, how do you do it? You take the 0.25 to the other side. That is, it becomes minus 0.25, then equal to 0. Okay. Let's do that. Let me clear this first. Clear. CLC. I hope I'm sharing MATLAB. Yeah. Okay. So first we had an example for F solve, right? I'm just taking it. I'm just copying it down here. Sorry, I F0. We had this function here. So e raised to exponential of minus x. And what was the rest of the equation? Let me just see. E raised to minus x sine 2x minus 0.5. Multiplied by multi sorry multiplied by sine 2x. I'll just put a bracket so that yeah. 2x minus 0.5, and this whole thing has to be subtracted by minus 0.25, right? This is the equation. Sine exponential of minus x sine 2x minus 0.5. Is this right? Sine 2x minus 0.5, and then it has to be taken to the other side, minus 0.25, and the interval is between 0 and 1. Let us try to do that. 0, sorry, 0, comma 1. Okay, this is the answer, 0.4518. Okay, if you have a doubt, we'll do one thing. X is equal to 0.4518. Let's keep it like that. And then we'll execute this command. We'll see what is the answer. Okay. You're getting it very, very close to 0. Okay. E raised to minus 0.5. So this is the answer, 0.4518. Anybody, any doubts? So this is how we use F0. For F0, you have to give an interval. For F solve, you have to just give an initial guess. And you can solve any nonlinear equation. And keep in mind that for a nonlinear equation to solve, basically, the MATLAB solver is equating it to 0. So the equation that you give also has to be equal to 0. Okay. Now the next question, it's another way. The friction factor is given to you, and you have to calculate the relative roughness. Reynolds number is also given to you. So I'll give you 2-3 minutes. If you have MATLAB, what you can do is you can just the turbulent function that you had, right? That you can just rearrange so that friction factor and Reynolds number is the input, and relative roughness can be given as an output. The same epsilon can be changed in such a way that relative roughness is the output that we get. Okay, I'll give you 2-3 minutes and then we'll discuss the answer. If you've got the answer, you can just put it in the chat box. Anyone got the answer? So you have to just rearrange the turbulent function equation. So this turbulent, we have this equation like this. So this takes Reynolds number and E by D ratio. Basically, Reynolds number and roughness as an input, and the output that you get is a friction factor. Now we have the other way around. So the same function I have just rearranged. Here, this is a new function, turbulent E by D. It takes Reynolds number and friction factor as input. Okay. Now what happens? Here you remember writing this equation. Sorry, I'll just close this out. Here you remember writing this equation like this. Here, this was a function of F. Okay, now we'll make this a function of E by D. So for that, you have to just write a function of E by D, and F is already given. F is, you get it from here. It is no more a variable. It is a constant. Now everything remains the same. And here Reynolds number and friction factor is there. And here the variable is E by D. That is why we mention it like this. The function, the variable that we are solving it for is E by D. Okay. And now what you do is you have to just F solve. It takes this function. Okay. And this is the initial guess. Initial guess means just a second. Yeah, initial guess for the E by D value. Okay, I'm giving an initial guess of 0.001. Let me just clear it. Yeah. Now, how do we run this? What you have to do is just copy this here. And what is the Reynolds number? Reynolds number is 1 lakh and friction factor 0.02. So that's what you have to just give the Reynolds number that is equal to 100,000 and friction factor 0.02. I hope you understood how did we write this function. Okay, earlier it was a function of F. Remember, if it was a function of F, this one you make it as a function of E by D so that the F and RE becomes the constants that you give or the inputs that you give. Now, when you run this, again, it will get solved. And finally, E by D, the roughness ratio is 4.2143 e raised to minus 0.04. So this is the final answer that you get. And this comes in the range of, just go to the PPT and then we'll see. Yes, sorry. This comes in this range, e raised to minus 0.04. So here in this range. Okay, 4 point something. That is 0.004213. It comes. The answer is B. Any doubts?
No, madam.
Yeah, sure. So if not, let us go to the next question. So this is also example with F0. Okay. So here you don't have to worry about the technicalities of the question, but imagine that it is similar to that we solved for the friction factor. So here you have a velocity, upward velocity V given as the function of the initial velocity U0, and M, that is the initial amount of fuel that is carried, the mass of it, and Q is Q is the fuel consumption rate, and G is the acceleration due to gravity, which is 10. So this is the equation that is given. U is a constant, U0 is a constant, M is a constant that is given, G is a constant, and Q is a constant. Now we have to use this to solve this equation. And the highlight is we wish to calculate the time at which the rocket reaches a velocity of 500. Okay. So here velocity is also given. 500 is also given. What is unknown here we are trying to solve? That is T. So first we have to rearrange this equation so that this total equation has to be equated to 0. And the variable you are trying to solve is not V, but T, time. Okay. And also for time, we have the bracket F0. If you remember, you have to give the lower limit and upper limit for the variable. So that I'm giving between 25 and 100. Okay. So the hints has been given to you in the question, and I've also told you the hints. Takes them 2-3 minutes. If you have MATLAB, try to code it. Otherwise, you can just take down a paper and try to write the equation. How should this equation be rearranged? And it's a simple line, right? How do you write this function so that it can be given to the F0? The function name here I've given it as rocket fun. It could be any function, but just try to write how the function looks like. Okay. And I'll discuss the answer in 2-3 minutes. How do we solve this question? I'll go to MATLAB. First, let me show how the function is written. Okay. This is a function that we're trying to solve using the f0. It takes in the variable t. So t is a variable that you're trying to solve for. So this equation has been given. The equation that we'll be running is f0. The variable is t and rocket fun is a function that we call and the limit is 2500, which is given in the question. Okay. Now the equation, what you have to do is, first of all, list all the constants that has been given, u, m, q, and g. All this has been given to you. Okay. Now rearrange this equation. How do you rearrange this equation? V is equal to u log m divided by m minus qt minus gt. This is equation, right? But you have to equate into 0. So what do you do? Take v to the other side. Okay. So basically, you'll be getting this equation as, uh, sorry. So v is equal to 500. Okay. So this is another way to do it. So we know v is equal to 500. So, uh, so what we'll try to do is, you can equate like this also to 0. Okay. V is equal to 500. And if you take the time, right? The time, 500 minus v. What will this equation look like? This will become 500 minus this equation. Okay. So we'll get the time. When we try to solve this equation, we'll get the time that corresponds to the velocity equal to 500. Basically, this is a function that we are trying to solve for. I hope you understood. Just a second. I'll just explain it again. You are writing 500. Yeah, did you get it?
Yeah,
Is
yes,
it? I'm sorry, it's not clear. I
I
hope you
got it,
understood.
ma'am.
Yeah, got it? Okay, fine. So this is what the equation that we are trying to solve, 500 minus v. Okay. Now we'll put this equation. FL is the output for this equation, rocket fun on the top. Now simply you have to run this command and you'll be getting the time at which the velocity hits 500. Basically, this equation will be equated to 0. Then you'll be getting the time equal to 89.8122. The second part of the question is, what was it? Just give me a second. Second part of the question is, for t equal to 25, what will be the function value? Okay. T equal to 25, you can just simply use that command that is given to you in the question. That is, you can use file is equal to, sorry, whatever is given to you in the question, you will be getting 448.3542. I hope this question is clear. Any doubts?
No doubts,
Okay.
ma'am. Okay,
Yeah. If
proceed.
not, we'll just move on to one more quick question using Epsol. This is an adiabatic flame temperature uh, in Kelvin. Burning methanol with 100% excess air in a furnace is given by the following expression. So the expression is given to you. You have to solve it using Epsol. Initial guess, try using any temperature. I've used a particular temperature in the code, which I'll show you later. Or else you can use any temperature for right now. Okay. And I'll give you 1 or 2 minutes and then we'll discuss the answer. How do we solve this question? We'll quickly go to MATLAB. You have to use Fsolve. Okay. So this is a function that we saw, the temperature is the variable that is there. Okay. This is some every solver like F-solve or F0, everything will have certain optim options. Okay. So you can just go to help F-solve. You'll see something like see also optim options. This will give you several options, okay? Whether you have to, you can increase the convergence criteria, you can decrease the convergence criteria, you can display the values, things like that you can do, okay? So right now I've just taken, written that display should be off, which means I don't want the solution found, those sentences to be displayed. I don't want that, okay? Initial guess I'm giving 1000, and then I use fsolve, the function that has been here with the t guess and the options, extra options. This is how you give. Okay, this options, this thing, you variable, you give it here. And finally, I print it out. Okay, let me just run this code for you. See, earlier we had all the solution found and all those sentences. Now that is not displayed. So that is how you do work with this optim options. There are several other optim options also. You can go see, you can just type the help command and you can see it for yourself. So this is how we use this fsolve for solving such kind of a problem. And just one more quick problem, and after that we'll end the session. Yeah. This is the last question. In a tubular reactor with axial dispersion and closed boundary condition, the Peclet number is related to the first and second moments of resonance distribution in a particular experiment. So this is how the Peclet number is calculated. Now solve this nonlinear equation with fsolve. Okay, due to time constraint, I'll discuss the answer right now. The first thing you have to keep in mind is that fsolve equates the equation to 0. The first is equation has to be converted in such a way that this will be equated to 0. Okay, you have to take the 0.25 to the other side. Now let us solve it. So this is the equation, as I said. The Peclet number is a variable that we are trying to solve. This is the equation, and 0.25 has to be taken to the other side so that the whole equation can be equated to 0. So minus 0.25. And again, optimum options, I'm giving display off. And this is a guess, initial guess for the Peclet number. And rest everything remains the same. So I'll just run this. And you get the Peclet number is equal to 7. Like this, you will have like several places, like while you're solving problems in the chemical engineering field or any field, you'll have several places where you'll have to solve non-algebraic equation. It might not be very straightforward. Then you can use the MATLAB functions. Which all functions did we see today? We saw fsolve, which has to be given an initial guess. Then we saw f0, which has to be given a bracket, okay, in which the answer has to be found out. Okay, so for example, just give me a second. Yeah, first we saw Newton-Raphson method. I gave you the code also for that. Then this is fsolve. You saw how this behaves. And then we saw f0. We also discussed how this bracketing method works. So I hope this was clear, and I hope you don't have any doubts regarding this week's recordings. And you can try to solve your assignments with whatever we have discussed. So in case you have any, if you don't have any questions, you can leave the session.
Okay, thank you.
Yeah.
Yes.
Thank you so much. Yeah.
A previous class, 1 hour class, I missed due to time
Okay.
adjustments.
Okay, that's
Uh,
fine. You can keep continuing the classes, and I've shared the recording also. Okay, so recording, I'll try to share it as soon as possible, but I can show you where the recording is. Okay,
okay.
yeah, just give a
Okay.
second. I'll just show you where the recording is. Okay, in this course page, if you go, in this course page, if you go here, okay, I have to log in, I think. Just give me a second. Let me just log in. Just a second. Yeah. I hope you can see the web page, and there is a section. Okay, below the course, there is a section called problem solving session recording. Yeah, this you can click here,
Okay, ma'am.
and then you will see a web page. Okay, these are my sessions. You will see the YouTube link for the previous classes, and also the PPT will be shared here. Okay, the PPT will be shared. Okay, it's not clear, Pavan, but I hope
Okay,
your doubts are
ma'am.
cleared. Yeah. Okay, then you can leave the meeting. Thank you so much, and I'll try to upload the recording. Okay,
Okay,
as soon as possible.
ma'am.
Yeah.
Classes. And after I
Actually,
will.
can you repeat it again, Pavan? I'm not able to hear
Okay,
you
ma'am.
properly. Okay.
Ma'am, hello.
Yeah. Yeah. Tell me. Yeah.
Yeah, I will after the classes, I will ask you
Okay, fine.
doubts in class, ma'am.
Yeah, sure. Okay, then.
Okay.
Bye.